How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You're walking through a city street at night. Rain begins to fall. Not just a generic video game rain, but a fine, misty drizzle that slicks the asphalt, catching the neon glow of a sign across the road. Each tiny droplet clings to the air for a moment before landing, distorting the light that passes through it. You look down and see the reflection of the entire street in a puddle. Every flickering sign, every passing headlight warped and rippling with perfect, fluid motion. The leather of your character's jacket has a subtle sheen, catching the ambient light differently than the rough concrete of the building next to you. Nothing is out of place. Nothing breaks the illusion. For a moment, you forget you're looking at a screen. You forget the millions of lines of code, the hardware humming away inside a box. You're just there. It feels seamless. It feels, for lack of a better word, real. We've all felt this, whether in a sprawling open-world game, a stunning animated film, or a hyper-realistic architectural rendering. We see this magic, we accept it, and we move on. We just assume there's a powerful computer in there, a fast brain, doing what fast brains do, making things happen quickly. But have you ever stopped to wonder how that actually works? What is the fundamental physical process that takes a sterile mathematical description of a world, a collection of coordinates and code, and transforms it into a living, breathing image 60 times every single second? What are the first principles that allow a machine to paint with light itself? Because the truth is, the device responsible for this magic doesn't think the way we assume. It isn't just a faster version of a normal computer brain. It's something else entirely. Something born from a completely different philosophy of problem solving. Today, we are opening the black box that sits at the heart of our visual world, and increasingly, the heart of our digital intelligence. We're talking about the graphics processing unit, the GPU. The magic we see today is so pervasive that it's almost invisible. We expect our phone screens to glide and animate with liquid smoothness. We expect to be able to edit high-definition video in real time on a laptop. In the world of cinema, the line between reality and computer-generated imagery has been completely erased. We can watch entire worlds, entire universes, born from nothing but data, and our eyes accept them as real. In medicine, surgeons can practice complex procedures on photorealistic digital twins of their patients. Car designers can sit inside a new model and see how the sunlight will glint off the dashboard before a single piece of metal is ever cut. All of this visual richness flows from the GPU. It's the engine of spectacle. For decades, that's what it was. A specialized piece of hardware with one primary job: to put pretty pictures on a screen as fast as humanly possible. It was the artist in the machine, and its impact on our culture, particularly through gaming, is impossible to overstate. It powered the evolution from the blocky, pixelated corridors of the 1990s to the uncannily realistic worlds of today. It was a race for realism, a relentless pursuit of more detail, more convincing light, more fluid motion, a race to close the gap between the virtual and the real. And for a long time, that's all we thought the story was. But we were wrong. To really understand the GPU, we have to go back to a time before it existed. A time when the very idea of real-time, three-dimensional graphics was a fantasy, a far-off dream confined to multi-million-dollar flight simulators and university research labs. Let's wind the clock back to the early 1990s. The personal computer is becoming a fixture in homes, and a new form of entertainment is exploding: the 3D video game. Titles like Wolfenstein 3D and Doom were revolutionary. They gave players a first-person perspective. the feeling of actually being inside the game world. But these worlds were abstract, made of flat, repetitive textures, 90-degree angles, and simple, direct lighting. They were compelling, but they were not realistic. The problem was the processor, the central processing unit, or CPU. The CPU is the general-purpose brain of a computer. It's designed to be a master of all trades, a flexible and powerful tool that can do anything you ask of it, from calculating a spreadsheet to processing a Word document to running the game's logic. In those early games, the CPU was doing everything. It was keeping track of the enemies, calculating the player's position, and, crucially, it was also responsible for drawing every single pixel on the screen. And that was the bottleneck. Think about what that entails. A computer screen, even back then, was a grid of pixels. A resolution of 640 by 480 pixels, low by today's standards, is still over 300,000 individual dots. To create a sense of smooth motion, you need to redraw that entire grid at least 30 times a second. That's over 9 million pixel calculations every second. Each of those calculations involves figuring out what object is visible at that point, what color it should be, how it's lit, and if it's in shadow. The CPU, for all its brilliance, was simply overwhelmed. It was like asking a single, genius architect to single-handedly lay every brick for a skyscraper. They might know exactly how to do it, but they can only lay one brick at a time. The sheer volume of work was insurmountable. This was the great wall that game developers and computer scientists were trying to climb. The holy grail was photorealism, but the math was brutal. A CPU is a serial processor. That word, serial, is key. It means it does things one at a time, in a sequence. It can be incredibly fast, moving from one task to the next in a fraction of a nanosecond, but it is fundamentally a linear thinker. Task A, then Task B, then Task C. When faced with the problem of drawing a 3D scene, it had to chug through the calculations for Pixel 1, then Pixel 2, then Pixel 3, and so on, for hundreds of thousands of pixels. It just couldn't do it fast enough to create a complex, believable illusion. The dream of immersive, real-time 3D graphics was being strangled by the very architecture of the computer. The world needed a new kind of brain. So, how do you solve a problem that is too big for one brilliant mind to handle? This is where a common misconception about the GPU comes in. Many people think of a GPU as just a superpowered CPU, a bigger, faster version of the main processor that's just dedicated to graphics. But that's not it at all. That would be like trying to build our skyscraper faster by just giving the single architect more coffee. The real solution isn't to make the one worker faster. It's to hire an entirely new kind of workforce. This is the moment where we open the box and find the first principle of the GPU: parallelism. Let's use an analogy. Imagine you have a single, brilliant university professor. This professor represents the CPU. You can give this professor an incredibly complex, sequential problem, like solving a deep calculus equation or writing a nuanced historical essay. They will work through it step by step, applying their vast knowledge and logic, and they will arrive at the correct answer. They are a master of complex, serial tasks. But now, imagine you give this professor a different kind of problem. You hand them a coloring book with 10,000 tiny squares and a simple instruction: color every square red. The professor is perfectly capable of doing this. They'll pick up a crayon, color the first square, then the second, then the third, methodically working their way through all 10,000. It's a simple task, but it will take them a very long time because of the sheer volume. They can only color one square at a time. Now let's try a different approach. Instead of the one professor, We gather an army of 10,000 schoolchildren. This army is our GPU. You can't ask this army to solve a calculus problem. You can't ask them to write a historical essay. Their individual skills are very limited. But you can give each child a single red crayon and point them to one single square in the coloring book. And you can give them all the same simple instruction. Color your square. On the count of 3, they all perform that one simple action simultaneously. 1, 2, 3, go. The entire book is colored in the time it takes to color a single square. This is the essence of parallel processing. It's about breaking a massive problem down into thousands of tiny, simple, identical tasks and having a massive number of simple workers execute them all at the exact same time. The GPU is not one brilliant professor. It is an army of thousands of tiny, specialized, simple processing units, which are called cores. While a high-end CPU might have 8, 16, or maybe a few dozen very powerful cores, a modern GPU has thousands of them. Each individual core is far less capable than a CPU core. It can't run an operating system or a word processor, but it is exquisitely good at one thing: doing simple math very, very fast. And when you have thousands of them working in parallel, they can solve a certain type of problem with staggering speed, the exact type of problem that was choking the CPU, the graphics problem. Drawing a scene is the ultimate parallel task. The calculation for the color of one pixel doesn't really depend on the color of the pixel next to it. It's a massive coloring book, and the GPU was the first machine to bring an army of schoolchildren to the task. So we have our army. But an army needs a battle plan. It needs a clear set of instructions to turn a bunch of abstract data into a beautiful image. This process is called the graphics pipeline, and it's the real story of how a GPU works. It's a multi-stage journey that every piece of a 3D world takes to get onto your 2D screen. It all starts with a model, a 3D character, a car, a tree, a building. In the computer's memory, these things are not solid objects. They are just a list of coordinates, a cloud of points in a virtual 3D space. These points are called vertices. Think of it as a giant cosmic game of connect the dots. The next step is to connect these dots to form simple shapes. For reasons of mathematical simplicity and efficiency, the shape of choice in computer graphics is the triangle. Everything, absolutely everything you see in a 3D-rendered world is ultimately made of a mesh of tiny, flat triangles. The smooth curve of a character's face, it's an illusion created by thousands of tiny, flat triangles, cleverly arranged and lit. A vast, rolling landscape, millions and millions of triangles. So the first job of the GPU's pipeline is to take this enormous list of triangles that make up the entire world and figure out which ones are actually visible to you, the player, from your specific point of view in the game. This first stage is called geometry processing. The GPU has to take the 3D coordinates of every triangle's vertices and translate them into the 2D space of your screen. It figures out perspective, making distant objects appear smaller, and it clips away anything that's off-screen or hidden behind other objects. This is a huge amount of mathematical heavy lifting, but it's still fundamentally a parallel task. The position of one triangle can be calculated independently of the others, so the army of cores can get to work, each one handling a batch of triangles and determining its place on the screen. Once the GPU has a 2D map of all the visible triangles, the next and perhaps most magical stage begins, turning this wireframe skeleton into a fully colored, lit and textured image. This process is called rasterization. The GPU takes the outlines of the triangles and fills them in, figuring out which pixels on your screen fall inside each triangle's borders. This is where we go from abstract shapes to the actual grid of pixels that you see. But what color should each pixel be? This is the most crucial question, and the answer comes from one of the most important concepts in modern graphics: shaders. A shader is a small, simple program that runs on the GPU's cores. Its only job is to tell the GPU what a pixel should look like. Think of shaders as the specific instructions we give to each of our schoolchildren in the coloring book analogy. Instead of just color it red, a shader might say, "Okay, for this pixel, check to see where the virtual sun is in the sky. Now, based on the angle of this surface, calculate how brightly lit it should be. Also, check the material property. Is it shiny like metal or dull like rock? Apply a texture map to it, which is like a wallpaper image, to give it the appearance of wood grain. Finally, check if another object is casting a shadow on this spot. Combine all of that information and output a final color value." Every single pixel on your screen gets this treatment, and because we have thousands of cores, we can run thousands of these shader programs simultaneously. One core calculates a pixel on a character's armor, figuring out the metallic glint of a virtual torch. At the same instant, another core is calculating a pixel on a stone wall, applying a rough texture and a deep shadow, and another is calculating the color of a wisp of smoke, making it semi-transparent. This is the heart of the GPU's power. It's a symphony of simple, parallel calculations, happening millions of times every fraction of a second. This is how we get rain-slicked streets and realistic shadows. It's not one genius artist painting the whole scene. It's an army of 10,000 tiny hyperfast artists, each given a single pixel and a simple set of rules to follow. From this massive, coordinated, but fundamentally simple effort, the complex and beautiful illusion of reality emerges. For decades, this was the story of the GPU. It was a remarkable, highly specialized piece of hardware that got better and better at its one job: running the graphics pipeline. Year after year, the army of cores got larger, faster, and more sophisticated. The shader programs they could run became more complex, allowing for ever more realistic lighting and material effects. The GPU was the engine of escapism, the master of visual spectacle. It was a story about gaming, special effects, and the relentless pursuit of digital beauty. And then, something completely unexpected happened. A few curious researchers, looking at this strange parallel architecture, had a thought that would change the world. They asked a simple question: what else can you do with an army of thousands of simple calculators? The answer to that question would trigger a revolution. The stage for the GPU's second act wasn't a game studio or a special effects house. It was a university computer science department where researchers were working on a completely different and, in many ways, much older problem: artificial intelligence. Specifically, they were working with artificial neural networks, a type of AI modeled loosely on the structure of the human brain. A neural network learns by processing vast amounts of data. To teach a network to recognize a cat, for example, you show it millions of pictures of cats. With each picture, the network makes a guess, and if it's wrong, it slightly adjusts the connections between its artificial neurons to get closer to the right answer next time. This training process is incredibly computationally expensive. Why? Because at its core, underneath all the sophisticated theory, the fundamental mathematical operation of a neural network is something called matrix multiplication. A matrix is just a grid of numbers, and training a neural network involves taking massive grids of numbers, representing the input data and the network's connections, and multiplying them together, over and over and over again. It is a mind-numbingly repetitive, but also fundamentally simple mathematical task. It is, in fact, the perfect parallel problem. For years, AI researchers had been running these calculations on CPUs, and just like the game developers in the 90s, they were hitting a wall. Training a large neural network could take weeks or even months on a single CPU. It was like asking our brilliant professor to multiply 2 phone books together by hand. They could do it, but it would be an agonizingly slow process. And this is the moment. The profound, landscape-altering aha moment. Around the mid-2000s, a few pioneering researchers realized that the math they were doing to train their ICE was structurally identical to the math that GPUs were doing to render video games. The process of multiplying matrices to update the weights in a neural network was the same kind of operation as multiplying matrices to calculate the color of a pixel based on lighting angles and textures. It was the same simple, repetitive task, repeated millions of times. The problem of teaching a machine to think looked, from a mathematical perspective, exactly like the problem of painting a beautiful picture. Suddenly, the GPU was no longer just a graphics card. It was a general-purpose parallel computing device. Researchers figured out how to bypass the graphics pipeline and speak directly to the army of cores, giving them tasks that had nothing to do with triangles or pixels. They started feeding their AI models to these gaming cards, and the results were breathtaking. A calculation that took a CPU weeks could be done on a GPU in a matter of days. A task that took days could be done in hours. The price-to-performance ratio was off the charts. An AI research lab could suddenly achieve the power of a multi-million-dollar supercomputer by stringing together a few $1,000s worth of consumer-grade video cards. This was the happy accident that fueled the modern AI boom. The entire deep learning revolution, the technology behind self-driving cars, voice assistants like Siri and Alexa, real-time language translation, and the large language models that are reshaping our world, was built on the back of hardware that was originally designed to make dragons look more realistic in the Elder Scrolls. The relentless, multi-billion-dollar consumer market for video games had, without intending to, created the perfect engine for artificial intelligence. The army of tiny artists we had built to paint light and shadow became an army of tiny thinkers, capable of learning, recognizing patterns, and generating new ideas. The unseen giant wasn't a single new principle. It was the shocking realization that the first principle we'd already discovered, parallelism, had applications so far beyond its original intent that it would redefine the future of technology itself. So we've taken a journey. We started inside a magically realistic virtual world. We saw it not as a seamless whole, but as a surface constructed from millions of tiny triangles. We looked closer and saw that the color and light of that world were not painted by a master artist, but calculated by an army of thousands of tiny, simple cores, each one a tireless worker executing a simple program. We pulled back the curtain on the illusion and found a first principle, the astonishing power of solving a problem in parallel. And then we saw how that one simple idea, honed for decades in the service of entertainment, became the key that unlocked one of the greatest technological pursuits of our time. Understanding the GPU is understanding a profound lesson about innovation. It's a lesson in how a tool can vastly outgrow its original purpose. The engineers who designed the first GPUs weren't trying to build artificial intelligence. They were trying to solve a very specific problem: how to draw a triangle on a screen as fast as possible. They were trying to win the graphics race, to deliver smoother frame rates and more polygons. Yet, in solving that narrow problem with a new philosophy of computation, They inadvertently created the foundational hardware for a new era. It shows us that progress is often not linear. It's combinatorial. It happens when an idea from one field, the brute force parallelism of graphics, collides with a problem in another, the computational bottleneck of neural networks. The GPU is a testament to the fact that you can't always predict the impact of a new technology. The most powerful ideas are often the most flexible, the ones that can be repurposed and reimagined in ways their creators never dreamed of. The virtual worlds we built for play, the intricate engines we designed to simulate light and physics for our amusement, have become the foundries where we are forging the minds of the future. The line between the painter and the thinker, the artist and the architect, has blurred into a single, unified army of processors, reshaping our reality from the echoes of worlds that were never real at all.
You've been listening to First Principles. Until next time, stay curious.